Welcome everyone to Rocks for Jocks. This podcast is intended for informational and entertainment purposes only. This channel is not intended to provide any financial advice, medical advice, or life advice. Now welcome to the show. All right, everyone. Today I'll be speaking with Robert Baxter. Robert is the founder and CEO of CBC Wind Energy, a company which produces wind turbines. Specifically, their goal is to place a number of these turbines and be able to deploy them in disaster relief areas, primarily across the Northeast, if I understand correctly. Before starting at CBC, Robert worked a few other management roles for software and marketing companies. At CBC, Robert has led the charge to obtain funding, get different projects off the ground, and lead the company through their starting stages. Robert, before I jump into questions, is there anything crucial I might have missed in there?
No, everything's good. I think that I appreciate the opportunity to be here, and we've got some exciting technology, and I'm looking forward to kind of spreading the word and letting people know about it.
Yeah, fantastic. So the first thing I'd love to ask about and just get your general take on is if you can maybe talk a little bit about the appearance of the turbines themselves that CBC makes, and if you can maybe share a little bit about why they look so drastically different from the generic large wind turbines that we're used to.
Yeah, sure. So the principle behind wind energy is pretty straightforward, right? The more power that you want to generate, the more wind you need to intercept. And traditional horizontal axis wind turbines do this. Most wind turbines do this by just making the blades bigger, right? They make the blades bigger to intercept more wind. But the bigger you make the blades, the more wind you actually need to get the blades moving. And then you have to figure out how to stop the blades. They need to be located either offshore or in the mountains. And then you need to build transport infrastructure to bring the power back to where it's being consumed. So our principle was, all right, now how do we develop a smaller wind turbine that can be embedded into the built environment that eliminates that transport infrastructure, right? Puts the power generation, co-located with the load, with the consumers who need the power, and then eliminate all of the objections, right? Shadow flicker, falling ice, wildlife hazards, noise, right? Eliminate all of those things that would prevent the technology from being embedded, adjacent to a building, right? Adjacent to where people live and work. So in order to do that, we use this enclosure, this wind intercepting enclosure that intercepts wind from all directions and creates a vortex. And if you ever seen like a potter and potter's hands on a wheel, it's the way our enclosure works. We shape this vortex and we change the shape of the chamber inside of our enclosure depending on or in response to the changes in the wind speed and wind direction, so that we've got this optimal vortex around a very purpose-built rotor in the center, and then that generates the electricity. So instead of using big blades, and there's a place for that, but in order to make wind turbine technology compatible with people and compatible with wildlife, we went in another direction. That's with our wind intercepting enclosure.
Cool. And how did you get started with that design? How did you even start to realize that there was kind of a niche for this opportunity and the technology change that came along with it?
Yeah, sure. So our company started as a consulting company, and we had some clients that were island resorts that were paying exorbitant amounts for electricity. And that meant that it was tough for them to offer amenities like air conditioning, like big television screens and things that consumed a lot of power, and still be competitive with other resorts that had a lower cost grid power. They contracted with us to identify a way that they could harness the wind to bring down their power costs. But the island was so regulated that the solar panels and traditional wind turbines, even non-traditional wind turbines, were out of consideration because the wildlife concerns, historical, architectural concerns, noise concerns because of the blades. They had one wind turbine on the island that was an annoyance. So we looked and we said, listen, there was no standard technology that would fit their constraints. And we concepted this technology. Said, you need something like this. And they're like, yeah, that's great. But, where do you get it? So we went off and we said, okay, with that idea, we said, let's commercialize it. And so we, over time pivoted the business and we refined the technology. We worked with local universities. We patented the technology. And now we're launching the tech and bringing it to market. So it started out of that need. And frankly, what we found was that enclosure that we talked about has a lot of other benefits. For instance, that becomes a very stable, compact geometry. And because of that, we saw storms and things like that. So, when we saw solar panels and wind turbines get trashed in these very high powered, storms, I said, we can make the enclosure survive 200-mile-an-hour winds. And we're like, all right. So we went off and did that. And then we were talking to local airports because airports have an abundance of wind. And we said, okay, we can make, because of this low, squat, close to the ground, stationary enclosure, no radar problems, we can make a turbine, a wind generator that is compatible with flight operations. So although we started with this resort application, the concept has kind of taken us in a couple different directions. And we found that we've got several other benefits. And those are the markets that those features, those capabilities have kind of funneled us towards this disaster relief, crisis response applications that we think people really need. We think there's a desperate need for this infrastructure in a box.
Yeah, that makes a lot of sense. And do you have a ballpark of, I guess, how much electricity is produced by some of CBC's turbines versus some of the bigger ones, which of course are more expensive and take longer to roll out and all of that? But yeah, I guess if you could kind of give us a scale of that.
Yeah, sure. So the cost of electricity is, just to take a step back. There's several elements, and one of the elements is the life of the technology, right? The life of the equipment, and another component is the infrastructure that's needed to put it in place and then transport the power back. So that varies from system to system, even for us, even application to installation to installation. So and then obviously how much wind is prevalent, but I can tell you this, our system, because again, we were designed to be a building system. And through our market research, we said wind turbines and even solar panels, especially solar panels, are designed with like a 20-year life. What, what property owners really expect is a building system that lasts the life of the building. When you buy a home or a building, you expect the plumbing to last. You expect the electrical system to last. You expect the alarm system to last the life of the building, which is much greater than 20 years. So we went back and we designed the structure to last decades, like 70, 80 years. That would drastically bring down the cost of power. The second thing is that a significant cost of the implementation of any wind project is the foundation, the permitting, and the transport infrastructure to bring it back. We eliminate or mitigate almost all of that. So that brings our costs way down. As a result, we're way below 10 cents a kilowatt hour in the best circumstances. In a case where there's a permanent installation in a windy area, we can estimate about 4 to 5 cents a kilowatt hour, which is pretty solid. But again, our primary application that we're going after, it's not so much the cost of the power, because we're going to areas where there is no grid. There is no, right. It either got wiped out in a storm or some other natural or man-made disaster. People need power for refrigeration of food, pump fresh water, preserve medicines, refrigeration. So that's the other side of the, and in that case, we don't have you know, people don't care about a system that's going to last for 80 years. They just need it now, and they might only use it for, 5 or 10 years or whatever, but they need something that's doable. So it's kind of a balance, right? But in a permanent application and in ideal locations, because of our durability and resilience, yeah, we can achieve very low costs of power.
Yeah, I know the lifetime of turbines is a problem that's discussed frequently as kind of a blocker in some cases. When I was in graduate school, I had a handful of coworkers and professors that were working on the soil structure interactions of offshore wind turbines versus the soil that's holding them up, and basically trying to get them to stay upright in water longer without degrading the turbine structure itself. Can you give us maybe a sense of scale of how many turbines you've been able to deploy to disaster relief areas? Maybe how many people you're able to service with those? Any numbers like that would just be interesting to hear about.
In a windy area, in the typical standard defined windy area. So each one of our 4 meter systems, and we call it a 4 meter system because the inlet is 4 meters high, 4 meters by 6 meters. Each one is designed to reduce about 750 kilowatt hours per month. For an average good sized house in the US, that might be just about one house. But in a lot of other areas where they have smaller homes and they draw less power, that could power maybe a half dozen or more homes. We're talking to folks in other areas of the world they figure that that might even power close to a whole little village. So one system, 750 kilowatt hours per month, but the systems are also designed to be daisy chained. So you can connect and scale. One of the challenges is, right, think about having one centralized big wind turbine. Now, in order to deploy something like that, inevitably you end up then with a need for heavy equipment, and you need cranes and trucks and to transport all of this stuff out there. And that's a problem, right? A lot of these places, if they need the power in the first place, they probably are not going to have this heavy equipment. They're not going to have perhaps even skilled trades or the parts and materials available to do this. So to meet the need, what our approach is to scale these things out. They're designed to be flown on cargo planes, towed by a pickup truck or a forklift or something like that, put in place, outriggers out, ballast it down. And again, if you need more than the 750 kilowatt hours per month, which is fine, you can scale out these modules. So you can picture, you know, on a large scale, big wind turbine Legos that you can snap together to get the power production that application needs.
That's fantastic. And then can you tell us a little bit about maybe where some of these wind turbines work best? In other words, which wind and atmosphere conditions you find them working best in, kind of how they're able to generate power most consistently.
Yeah. So folks look at, you know, they look at around, they say, oh, it's windy here, right? So what does that mean? Well, our systems are designed to be relatively tolerant of turbulence, but you still need to have wind energy. So if you're in a valley, if you're surrounded by trees or up against buildings, that's not going to work, right? So if you are in the position of the actual wind turbine, you want to be able to see sky. You want to be able to look out and see that you've got unobstructed wind for 300 feet. So picture like a football field area. So you've got the wind coming along the ground that can intercept. Now, uh, depending on where you're at in the world, most places, 50%, 60, maybe even 70% of the time, wind is below 10 miles an hour. There are windy places where maybe in the afternoon you get gusts of like 13, 14, 15 miles an hour, and then you get storms. But most of the time, the wind is very light. So what we've done is to adjust to that. So that's the sails are out there. They intercept a large amount of wind. Our rotor is very lightweight, and we've got a variable load generator array. Basically, this connects most of the generators at very low wind speed. So you're just spinning. We're always generating power, even if the wind only has a little bit of power to give. We harness that power. So what kind of conditions are ideal? Well, you're on a beach or a flat island or a prairie, and you got like 15 miles an hour, blowing all of the time. But we know that that's not the case. And so what we've done is, say, okay, what do we do if we don't have laminar wind? What if the average wind speed is 8 or 9 miles an hour? And how do we handle that? And again, remember, we're also close to the ground, right? Our system is designed to be ground mounted. And so we're designed to be more tolerant of those types of wind conditions. So we're pretty flexible.
That's so cool. I think I saw on your website somewhere that some of the turbines are designed specifically for low wind environments. I was wondering if you could tell us maybe a little bit more about technically how the rotors are designed to work at low wind speeds versus high wind speeds.
Well, the way we do that, well, I'll tell you a couple things. So the first one is like we intercept a lot of wind, right? So, and then that means we have to make the enclosure strong at high wind speeds, but that's okay. We know what to do, how to slow the system down at high wind speeds, which we could talk about later. But but we intercept a lot of wind, and again, most wind turbines, well, almost every other wind turbine, if you've got a wind turbine size for 10, 20, 100 kilowatts, they've got a 10, 20, or 100 kilowatt alternator generator sitting behind that. So to get the thing started, you have to turn and overcome that entire load. And what we've done is take another approach. What we do is say, okay, and again, this falls out of our structure because our rotor is mechanically isolated from the, from the drivetrain. We can connect and disconnect and have redundant alternators and do all sorts of things. And so that not only improves the resiliency of our system, but what it does is it allows us to say, okay, again, I have this enclosure size for 9 kilowatts, but maybe at the beginning I only have, a 200-watt alternator on that has almost no load on it. So that at the very low wind speeds, we can still generate what little power the system has to offer. Then the other issue is when you have high winds, what do you do? And again, our system is designed with that, the way we form and shape that vortex to shed a lot of the wind in order to allow it to pass through our enclosure without impinging on the rotor. So we do that. And then finally, I think the other key thing is if you look at a traditional wind turbine, and again, we want to work with, we don't claim that we're going to replace any other technology. We're a complementary technology to traditional wind, but also to solar. We want to work in conjunction with all of these. But one of the things that makes us different is I always use the analogy of if you've ever gone to like a banquet or a wedding and you've got waiters and busboys. The waiter is walking through and you got all the tables filled. The waiter's got a tray on one arm and is kind of bobbing and weaving and the tray is balanced. And don't take any of the glasses off. Let the waiter do it because that'll upset the tray. Then you have the busboy come out afterwards. The busboy's got a very low center of gravity, got the tub below his waist with two hands. Those are fundamentally the two design philosophies for wind turbines. Most wind turbines are designed with the waiter philosophy. You've got a single rotor mounted to a single hub attached to the drivetrain. And we're more the busboy. We've got a rotor that's pinned top and bottom within our enclosure, mechanically isolated from the drivetrain. So this thing can do all sorts of stuff. You can throw stuff at it, you can poke holes in it, you can do whatever you want. It can get out of balance. It's designed for that. And then and still survive because we're not transmitting any vibration through the rest of our powertrain or to the ground or whatever that is. So we've got a much more sturdy, robust architecture, mechanical architecture to work from. So, that is, again, not that one is better than the other. It's just they have different applications.
Thank you so much. And then one more question on the technicals. Do you see the turbines being impacted by any other environmental factors like heat or rain or snow or anything like that?
So our first contracts have been working with the United States Air Force to go into this contingency response or disaster response, disaster recovery. And so all of the materials are designed to be just super durable. I mean, the stuff that we're using very unconventional materials for most of the components, and they're just designed to last, decades and decades in the most extreme environments. To give you a sense, like our aero surfaces are mostly made of a membrane similar to what is used to line the basins for, chemical runoff and stuff like that. So when it comes to UV radiation and temperature extremes and all sorts of environmental extremes, we are, we're over designed. But again, because the problem that we're trying to address is that we want to be able to go into the most austere environments, take whatever punishment is there and still be able to last for decades if that's what's needed.
Great. Yeah, I definitely agree with that philosophy of over designing rather than under designing for those environmental impacts. So, really appreciate that. Another topic I wanted to touch on here was the environmental impact of wind energy itself. Could you maybe tell us a little bit about how CBC turbines see themselves fitting into the environment and any impacts those turbines may have on the stuff around them?
Yeah, sure. I mean, obviously, we're trying to provide an alternative source for power, an alternative to traditional fossil fuels for power. Uh, and like I mentioned before, though, we don't think that we're going to be the only source. We see ultimately the solution on a large scale to be a diversified or distributed portfolio of energy generation. That's, yeah, everything. Yeah, yeah, yes, natural gas, but also wind and maybe big wind and distributed wind and solar and all of this, right? So we see a very distributed energy portfolio, and we think that there's a role for our technology to play in that. So that's the first thing. The second thing is once you get to that point, we want to do no harm, right? So we want our technology to be not only built environment friendly, but also wildlife friendly. So we've gone to extremes almost to make our technology friendly to both ground and flight, birds, bats friendly. If you look at like different studies, for instance, black is a good color, right? White is not a good color. Most wind turbines are white because then it doesn't show up in nature and it attracts bats. So fundamentally, our wind turbines are black. That I mean, it sounds silly, but that's one thing. Next is again, we're designed to be a stationary enclosure. So when you look at bird strikes, all right, and so you have collisions and you have strikes. So a strike is when a moving portion of your system hits something else. So a blade hits a bird. Well, our rotor is inside of a stationary enclosure and we're mounted low to the ground. So we've eliminated the possibility of strikes. And we had a system deployed at the University of Rhode Island's Bay campus for many years. And, the way that you measure bird strikes is by counting carcasses on the ground. And after I think it was 3 or 4 years, we had zero issues, right? So there were no evidence, zero evidence of any bird strikes. So then the other issue is collisions. Do things fly into your system? Like that's a problem with traditional horizontal axis wind turbines, the monopole mast, bats. For some reason, they're attracted by the white monopoles and they fly into them. But again, we're close to the ground. We don't look curious to them because of the size and the shape and the color. And again, so no issues there. Another, the two other issues you have like noise and then artificial illumination or any kind of reflected illumination. And our system is mostly silent. Like you can stand right up against it and the system doesn't emit any noise beyond or above the ambient noise of the wind going by you. So we've addressed the noise pollution. Not emit any artificial illumination. So we've gone through these multiple potential wildlife hazards to be environmentally friendly. And then again, probably the biggest one is that we're designed to be mounted within the built environment. So on top of a building, on top of a parking lot, or in a field like a farmer's field or something after storm environment or on an airport. And so we don't need to carve or lay any cable from the mountains or from the ocean back in to the consumers. And we're not disrupting any habitat out in an undisturbed area of the world where we're already in the built environments. Those are probably the top ways that we have tried and we think that makes the most sense to be truly, environmentally friendly.
Yeah, that makes a lot of sense. Specifically within the urban environment, I'd be curious, have you or your team found yourselves running into any challenges in terms of, I don't know, rodents or birds or anything like that kind of nesting in the turbines?
Not in the enclosure. And we have taken some steps towards making the system rodent and insect. The big thing is rodents and insects. It's very difficult to say that you've accomplished it 100%. Quite, I think we're pretty solid in terms of they don't. Nothing really wants to nest or live within us, so we're concerned about it, and we think we've addressed it. But that's a tough one.
Yeah, absolutely. The next question I have for you is, do you see any kind of trends or technological advancements for wind energy or just energy in general, maybe in the next 10 years or so?
Well, uh, I don't know if I see the trend, but what I would hope would be a trend is that the wind industry has three significant obstacles. Believe it or not, the wind industry is very heavily regulated. And so there are several barriers, I mean, significant barriers to entry with a new technology. And you can come up with an idea, but in order to commercialize it, in order to connect it to the grid, in order to get those approvals, is tough. This kind of gets to the second obstacle. We've got a very skeptical customer base because, again, early on, there, and I'm talking about 10, 20 years ago, there were a lot of folks, new businesses who thought they had something and they didn't. Let's just to put it that way. So it's made people very hesitant to be early adopters of new technology. So the system responded kind of overcompensated. On the one hand, they put up a significant regulatory barrier, which is very difficult to overcome. And then the second is that the customer base is very skeptical. So you've eliminated between the two, you've eliminated early adopters. And right, the strength of in our history, the nation's history has been this combination of innovation and the presence of early adopters to try it out, right? So you've got like the Model T, and folks were ready to try the Model T, right? You need one, you need both. You can't have one without the other, you know? So you had Samuel Morse with the telegraph and folks who were willing to try it out. And then wait, in his case, it was the government, right? So you need to, and the wind industry is kind of struggles because of that. And then the last thing is the presence of capital. To overcome those things, you need a lot of capital, and the investors are skeptical, and it's just very difficult. So the trend, that I would like to see at least is an openness or willingness of some early adopters to come out and say, "Hey, this is new technology. Let's try it in these other applications." And one of the reasons why we've established our beachhead market and for our technology in this disaster response, disaster recovery market is because the pain point is so high that they're willing to try new technology. So that's that, so we overcome that barrier. So it's not a trend that's happening, but it's a trend that I would like to see the presence of more early adopters.
Great. Yeah, absolutely. And then, do you have any advice for new entrepreneurs or new companies in the renewable energy space, maybe trying to push forward their business problems, anything like that?
I would say be flexible and be persistent and constantly question yourself. So in reverse order, you're going to set up some assumptions, test those assumptions, really understand your market. And then even when you understand it in January, double check in June, double check in July, right? Because the world is changing. Constantly work to understand the opportunity and has the opportunity changed and what elements of the opportunity are out there that you may have missed. Be flexible because as this comes up and you're constantly questioning, you're like, all right, I know plan A was this. But frankly, we're on plan L because as we got into it, either the regulatory environment changed or another opportunity came up, or there was a capability in our technology that we really didn't appreciate. And so be flexible. And then once you got that, be persistent, keep plugging away every day, make a little forward progress, towards that goal. You don't have to get there all at once. I always say, I'm the tortoise, I'm not the hare. And our goal is just to slow and steadily and persistently get to the finish line and, we'll do it. So constantly work, constantly read to understand your market, be flexible and be persistent.
Great. And then the last question, it's kind of a fun one if you want to answer. Were there ever any kind of alternative career paths you may have seen yourself going down if things had gone slightly differently?
This is my alternate career path. So,
Yeah, fair.
so I have my undergraduate degrees in electrical engineering. I realized real quick that the engineers didn't make the decisions. My graduate degrees in finance, I had a ton of fun as a director of marketing, which involved not just marketing communication, but we were involved in business development and product marketing, product development. And I've gotten like 14 or 15 patents. And then the consulting thing. And again, I've been so blessed. I've done, I've had some real fun over the course of my career. This is the alternate career. I'm like, we had this, it's been slowly getting it off the ground and we're having a lot of fun doing it. So yeah, this is it.
That's such a nice way to put it. Again, Robert, thank you so much for joining us today. Is there anything else you want to say to anyone listening?
No, I appreciate it. Thanks so much. Check out our website, cbcwindenergy.com. And, if you're an early adopter out there, give us a call. Thanks so much.
Thanks again, Robert. If you enjoyed listening to this episode, please give the channel a like or a subscribe or a follow, depending on where you're listening. Any reviews are really appreciated and help more than you could ever know.